This video comes to you by Nicole Christopoulos
and Todd King,
and it's for our course Physics NYC. So first off, the name Schrödinger brings a few things to mind. What do we know exactly? Well, first off, we know that he was smart. We also know that he performed a cat experiment. Other than that, for the most part, we don't know much. But we will shortly. So this brings us to Schrödinger's cat experiment. And for starters, we'd like to apologize for our terrible drawings. Schrödinger's cat experiment was putting a cat into a box and then putting a vial of poison. At some point within the hour, the poison was said to potentially go off. The odds, 50-50. Within that hour, you had two possible outcomes, if of course you were to open the box. The first is that the cat goes about its normal activities within the box. It's alive, it's happy, the vial does not go off. The second outcome is that the cat dies. Poor Schrödinger's cat. So the limit of the cat experiment as it approaches infinity and gets repeated an infinite number of times is a 50-50 ratio if the box were to be opened. Number 1, the dead cat, and number 2, the cat's alive. So before we open the box, the cat could be thought of as both dead and alive. But after opening the box and satisfying our curiosity, the cat has to either be alive or dead. So what exactly was Schrödinger thinking? The probability of finding the cat, dead or alive, is the same as the probability of finding a particle at that point. And in Schrödinger's words, the psi function of the entire system would express this by having in it the living and the dead cat mixed or smeared out in equal parts. We'll now be moving on to defining a couple of terms and giving a couple of equations.
Alright, so this first equation we have here is capital psi of x, y, z, t. Take the absolute value of that and we square it. And this function tells us the probability of finding a particle at a certain position at a certain time. And it should be noted that if smaller psi, lowercase psi, is used, that it's only a function of position and not time.
We're now going to be defining the wave function, which is a little trickier to define, and it's why it's defined second in most textbooks. As you can see, there's no square and there's no absolute value signs, but once again, it is in the fourth dimension and it is a capital psi, and it basically describes all spatial properties of this particle, whether it be an electron or a proton. So these are not limited to, but they include momentum, kinetic energy, and potential energy.
Alright, so if we take our first equation and look at it again, but we're defining it for a given volume. So we use the exact same formula and we just multiply it by dV, which is a certain volume. As volume increases, naturally the probability of finding a particle in that volume also increases. And eventually, as you get to a volume of the universe, the probability of the particle appearing somewhere in that universe is 1.
So now moving on to stationary states, what they'll probably remind most of you of is chemistry. So in chemistry we have orbitals, so they're stationary states. They're states in which the energy does not change because of time. It's a fixed state, which is why they're called stationary states. And the equation that applies is this one, and it should be noted that n can never be equal to 0 because the probability of finding a particle nowhere is not 0, cannot be equal to 0. It's always positive 1, integers, positive 2, positive 3, positive 4.
Alright, so next we have the Schrödinger's equation for a 1D box. This tells us the energy for a given stationary state, which is n, that a particle has in a 1D box. So we have E sub n, which is the energy. We have n, which is a stationary state, which could be 1, 2, 3, 4, etc. H is Planck's constant. M is the mass of either electron or proton, and L is the length of that box in one dimension.
Finally, we have Schrodinger's equation, which of course looks extremely complicated and hard to define, but what the point is and what we need to understand for this course is that the first part is equal to kinetic energy, the second is potential energy, and finally that's equal to the total energy. And this of course reminds us of conservation of energy, so as the kinetic energy increases, the potential has to decrease, and it's conserved in a total energy matter. Thankfully, for this course, we don't actually need to apply this equation, but moving on, we're going to be applying this equation in a problem just shortly.
Alright, so here we have an example of a problem we could see. So, an n equals 1 to n equals 3 transition from an electron trapped in a rigid box produces a 240 nanometer photon. What is the width of the box? So, here are some relevant numbers that we know already. So here we have the solution to the problem. First of all, we're going to find the change in energy. We do this because there's a transition from the n equals 1 to n equals 3 level. So delta E is equal to Planck's constant, 6.63 exponent negative 34 joules times second, times the speed of light, 3 exponent 8 meters per second, and that's all divided by our wavelength, and our wavelength is 240 exponent negative 9 meters, and this value turns out to be 8.2875 exponent negative 19 joules. So now that we have the energy, we can apply this to our first equation, which is E sub n is equal to n squared h squared divided by 8ml squared. So we're going to bring this in here. So we'll get 8.2875 exponent negative 19 is equal to, so for n, since we're going from n equals 1 to n equals 3, we're going to take the square of 3, so 9, and the square of 1, which is 1. So we'll have 9 minus 1, which will turn out to be 8 afterwards, and it'll cancel with this 8 down here. Then we have Planck's constant squared, 6.63 exponent negative 34 joules second, divided by 8 times the mass of an electron, which is 9.11 exponent negative 31 kilograms, and times the length, which is what we're solving for. So by multiplying both sides by L squared and then dividing both sides by 8.2875 exponent negative 19, we end up with L squared is equal to 5.822 exponent negative 19 meters, and by taking the square root of this side, L is equal to 7.63 exponent negative 10 meters. And this is our answer.